Yes, connecting a 230-volt motor to a 240-volt service is a concern. While a 20 horsepower motor is rated for 208 to 230 volt operation, it is not designed to operate continuously at 240 volts. Operating a 230 volt motor at 240 volts can cause several issues. Firstly, overheating can occur. The motor will draw more current at 240 volts than it would at 230 volts, which can lead to overheating of the motor windings. This can damage the motor insulation and shorten its lifespan. Secondly, reduced efficiency is a concern. A motor operating at a higher voltage than it is rated for will be less efficient, which means it will consume more power to produce the same output. Thirdly, voltage spikes are a potential problem. The high leg, which is the orange wire, in your three-phase service can create voltage spikes that can damage the motor if it is not properly connected. It is highly recommended that you have a qualified electrician verify the voltage at the motor terminals and ensure that it is not exceeding 230 volts. If the voltage is too high, you can consider the following options. 1. Install a transformer. A transformer can be used to step down the voltage from 240 volts to 230 volts. However, this can be expensive and may not be practical in all cases. 2. Use a voltage regulator. A voltage regulator can be installed to maintain a constant 230 volts at the motor terminals, regardless of fluctuations in the incoming voltage. This is a more cost-effective option than a transformer. 3. Contact the motor manufacturer. The motor manufacturer may be able to provide recommendations or modifications to make the motor suitable for 240 volt operation. By addressing this issue promptly, you can help prevent damage to your new equipment and ensure its safe and efficient operation. To expand upon these points, let's delve into why each issue arises and how the suggested solutions mitigate those risks. The issue of overheating stems from the fundamental relationship between voltage, current, and resistance in an electrical circuit. According to Ohm's law, current is directly proportional to voltage and inversely proportional to resistance. When a motor designed for 230 volts is subjected to 240 volts, the current flowing through its windings increases, assuming the resistance remains constant. This increase in current leads to higher power dissipation in the form of heat, following Joule's law, which states that power is proportional to the square of the current. The motor's insulation is designed to withstand a certain level of heat. However, prolonged exposure to excessive heat can degrade the insulation material, leading to short circuits, ground faults, and ultimately, motor failure. The lifespan of the motor is significantly reduced due to this thermal stress. To put it into perspective, consider the insulation as the protective coating on the wires within the motor. Overheating is like repeatedly bending a paperclip until it breaks. Each instance weakens the structure and at some point it finally snaps. In this case, the heat deteriorates the wire's insulation, increasing the risk of failure and reducing the motor's overall life expectancy. Reduced efficiency is another crucial factor. Motors are most efficient when operated at their rated voltage. When a motor operates at a voltage higher than its rating, its magnetic core becomes saturated. Magnetic saturation means that the core material can't effectively channel the magnetic flux produced by the windings. As a result, a larger portion of the electrical energy is converted into heat instead of mechanical work. This inefficiency translates directly to increased energy consumption and higher operating costs. Moreover, the motor's power factor, which is a measure of how effectively the motor uses electrical power, also decreases, making the motor less efficient and potentially causing issues with the power grid. In essence, you are paying more for the same amount of work done, while simultaneously stressing the motor and potentially disrupting the power grid. As an analogy, imagine using a car that's running on the wrong fuel. It might still run, but it won't run as smoothly or efficiently, and it will likely consume more fuel and could damage the engine. Voltage spikes associated with a high-leg delta system are also cause for concern. In a high-leg delta system, one phase, often colored orange, has a voltage to neutral that is significantly higher than the other two phases. This high leg can introduce transient voltage spikes that can damage the motor's windings and control circuitry. These spikes can be caused by switching events, lightning strikes, or other electrical disturbances. If the motor is not properly protected, these spikes can puncture the insulation and cause catastrophic failure. Voltage spikes are like sudden jolts of electricity that the motor is not designed to handle. These jolts can cause immediate and lasting damage to the motor's sensitive components. Now, let's consider the recommended solutions. The first is installing a transformer. A transformer is a device that transfers electrical energy from one circuit to another through electromagnetic induction. It consists of two or more coils of wire wound around a common magnetic core. By varying the number of turns in each coil, the transformer can step up or step down the voltage. In this case, a step-down transformer is used to reduce the 240-volt service voltage to the motor's rated 230 volts. This ensures that the motor operates within its design parameters, preventing overheating and reducing the risk of damage. While transformers can be expensive, they provide a reliable and effective solution for voltage matching. They are particularly useful in situations where the voltage difference is significant or where the voltage fluctuates frequently. Think of a transformer as a translator between two different electrical languages. It takes the incoming voltage and converts it to a voltage that the motor can understand and use safely. The second solution is using a voltage regulator. A voltage regulator is an electronic device that maintains a constant output voltage despite variations in the input voltage or load current. It uses feedback control to adjust the output voltage as needed. Voltage regulators are typically more compact and less expensive than transformers, making them a cost-effective solution for voltage stabilization. They are particularly useful in situations where the voltage fluctuations are relatively small or where space is limited. A voltage regulator acts like a volume control for voltage. It continuously adjusts the voltage to keep it at the desired level, regardless of any changes in the incoming voltage. This ensures that the motor always receives the correct voltage, preventing damage and improving efficiency. The third solution is contacting the motor manufacturer. The motor manufacturer may have specific recommendations or modifications to make the motor suitable for 240-volt operation. For example, they may be able to provide a modified motor with high voltage insulation or a different winding configuration. They may also be able to provide instructions on how to properly connect the motor to a high-leg delta system to minimize the risk of damage from voltage spikes. Consulting the motor manufacturer is like asking the motor's doctor for advice. They know the motor best and can provide the most accurate and reliable guidance. In addition to these solutions, it is also important to ensure that the motor is properly grounded and protected by appropriate overcurrent devices such as fuses or circuit breakers. Proper grounding provides a low resistance path for fault currents, protecting the motor from electrical shock and reducing the risk of fire. Overcurrent devices protect the motor from damage caused by excessive current flow, such as that caused by a short circuit or overload. These protective measures are essential for ensuring the safe and reliable operation of the motor. Think of grounding as the motor's safety net, protecting it from falls. And overcurrent devices are like the motor's guardian angels, protecting it from harm caused by excessive electrical activity. Let's dive deeper into the technical specifications and considerations for each of these solutions, starting with transformers. When selecting a transformer for this application, several factors need to be taken into account. Firstly, the transformer's volt amp, abbreviated as voltamps, rating must be sufficient to handle the motor's full load current. The volt amp rating is a measure of the transformer's capacity to deliver power. It should be at least 125% of the motor's full load volt amp rating to account for starting current and other transient loads. Secondly, the transformer's voltage ratio must be appropriate for stepping down the voltage from 240 volts to 230 volts. A transformer with a voltage ratio of 240 to 230 would be suitable for this application. Thirdly, the transformer's impedance should be carefully considered. The impedance is a measure of the transformer's opposition to the flow of alternating current. A transformer with a low impedance will provide better voltage regulation, but it may also be more susceptible to short-circuit currents. A transformer with a high impedance will provide poor voltage regulation, but it will be more resistant to short-circuit currents. The impedance should be chosen to balance these competing considerations. Fourthly, the transformer's insulation class must be adequate for the operating environment. The insulation class is a measure of the transformer's ability to withstand high temperatures. A transformer with a higher insulation class will be more resistant to overheating and will have a longer lifespan. Fifthly, the transformer's enclosure should be appropriate for the installation location. The enclosure protects the transformer from environmental factors such as dust, moisture, and corrosion. A transformer installed in a damp or corrosive environment should have a weatherproof enclosure. In addition to these technical specifications, it is also important to consider the transformer's efficiency. A more efficient transformer will consume less energy and will have lower operating costs. When it comes to voltage regulators, there are also several factors to consider. Firstly, the voltage regulator's input voltage range must be compatible with the 240-volt service. The input voltage range is the range of voltages that the regulator can accept as input. The regulator should be able to operate reliably over the entire range of expected input voltages. Secondly, the voltage regulator's output voltage must be adjustable to 230 volts. The output voltage is the voltage that the regulator provides to the motor. The regulator should be able to maintain a constant output voltage even when the input voltage or load current varies. Thirdly, the voltage regulator's current rating must be sufficient to handle the motor's full load current. The current rating is a measure of the regulator's capacity to deliver current. It should be at least 125% of the motor's full load current rating to account for starting current and other transient loads. Fourthly, the voltage regulator's response time should be fast enough to correct for voltage fluctuations quickly. The response time is the time it takes for the regulator to adjust its output voltage in response to a change in the input voltage or load current. A faster response time will provide better voltage regulation. Fifthly, the voltage regulator's protection features should be adequate to protect the motor from damage. The protection features may include overvoltage protection, undervoltage protection, overcurrent protection, and short-circuit protection. These features will help to prevent damage to the motor in the event of a fault. In addition to these technical specifications, it is also important to consider the voltage regulator's efficiency. A more efficient voltage regulator will consume less energy and will have lower operating costs. Consulting with the motor manufacturer is a crucial step in determining the best solution for this application. The motor manufacturer can provide specific recommendations based on the motor's design and operating characteristics. They may be able to provide a modified motor with high voltage insulation or a different winding configuration that is better suited for 240-volt operation. They may also be able to provide instructions on how to properly connect the motor to a high-leg delta system to minimize the risk of damage from voltage spikes. The motor manufacturer may also be able to provide guidance on selecting the appropriate transformer or voltage regulator for this application. They may have preferred suppliers or specific models that they recommend. In addition to the technical aspects, it is also important to consider the cost of each solution. Transformers are typically more expensive than voltage regulators, but they provide a more robust and reliable solution for voltage matching. Voltage regulators are less expensive, but they may not be suitable for all applications. The cost of consulting with the motor manufacturer should also be taken into account. However, this cost is typically small compared to the cost of replacing a damaged motor. Ultimately, the best solution will depend on the specific circumstances of the application, including the voltage difference, the voltage fluctuations, the load current, the operating environment, and the cost. By carefully considering all of these factors, you can select the solution that will provide the best performance, reliability, and value for your money. Remember, safety is paramount when working with electrical equipment. Always disconnect the power before working on any electrical components. If you are not comfortable working with electrical equipment, consult with a qualified electrician. Ignoring these precautions can lead to serious injury or even death. It's also vital to understand the implications of using a high leg delta system. The high leg, typically identified by an orange-colored conductor, presents a unique voltage relationship compared to the other two phases. While the voltage between the other two phases is 240 volts, the voltage between the high leg and neutral is approximately 208 volts. This voltage imbalance can create complications if not properly managed. Equipment not designed for this voltage configuration can be damaged if connected to the higher leg. Therefore, it is imperative to clearly identify the higher leg and ensure that only equipment specifically designed to operate with it is connected to the phase. Clearly labeling the high leg and providing training to personnel working with the electrical system can help prevent accidental misconnections and potential equipment damage. Furthermore, the National Electrical Code, NEC, provides guidelines and regulations for working with high leg delta systems. Adhering to these regulations is crucial for ensuring the safety and proper functioning of the electrical system. Consulting with a qualified electrician who is familiar with high leg delta systems is highly recommended to ensure compliance with the NEC and to avoid any potential hazards. It's also important to consider the impact of voltage imbalance on the motor's performance. Voltage imbalance occurs when the voltages between the three phases of a three-phase system are not equal. This imbalance can cause several problems, including increased motor current, reduced motor torque, and increased motor heating. The NEC specifies limits for voltage imbalance in three-phase systems. If the voltage imbalance exceeds these limits, it should be corrected to prevent damage to the motor and other equipment. Voltage imbalance can be caused by several factors, including unbalanced loads, faulty transformers, and incorrect wiring. Identifying and correcting the source of the voltage imbalance is essential for maintaining the reliable operation of the electrical system. Regular monitoring of the phase voltages can help detect voltage imbalance early, allowing for prompt corrective action. In addition to voltage imbalance, harmonic distortion can also affect the motor's performance. Harmonic distortion is the presence of unwanted frequencies in the electrical waveform. These frequencies can be caused by nonlinear loads, such as variable frequency drives, electronic ballasts, and computers. Harmonic distortion can cause several problems, including increased motor heating, reduced motor efficiency, and increased stress on the electrical system. Harmonic filters can be used to reduce harmonic distortion. These filters are designed to block or attenuate the unwanted frequencies. Selecting the appropriate harmonic filter for a given application requires careful consideration of the harmonic content of the electrical waveform. Regular monitoring of the harmonic distortion can help detect problems early, allowing for prompt corrective action. When evaluating the motor's performance, it's crucial to consider its nameplate ratings. The nameplate provides essential information about the motor's operating characteristics, including its voltage rating, current rating, horsepower rating, speed, and efficiency. The motor should be operated within its nameplate ratings to prevent damage and ensure reliable performance. Operating the motor outside of its nameplate ratings can lead to premature failure and void the warranty. The nameplate also provides information about the motor's insulation class, which is a measure of its ability to withstand high temperatures. The motor should be operated within its insulation class to prevent overheating and extend its lifespan. The nameplate also provides information about the motor's service factor, which is a measure of its ability to handle overload conditions. The motor can be operated at its service factor rating for short periods of time without damage. However, continuous operation at the service factor rating can reduce the motor's lifespan. Regular inspection and maintenance are essential for ensuring the reliable operation of the motor. The motor should be inspected regularly for signs of wear and tear, such as cracks, leaks, and corrosion. The motor's bearings should be lubricated regularly to prevent excessive wear. The motor's windings should be tested periodically to ensure that they are not damaged. The motor's cooling system should be checked regularly to ensure that it is functioning properly. Any problems identified during inspection should be corrected promptly to prevent further damage. Keeping accurate records of motor inspections, maintenance, and repairs can help track the motor's performance over time and identify potential problems early. In summary, connecting a 230-volt motor to a 240-volt service requires careful consideration and proper planning. While it may be possible to operate the motor at 240 volts, it is important to take steps to mitigate the risks of overheating, reduced efficiency, and voltage spikes. Consulting with a qualified electrician and the motor manufacturer can help ensure that the motor is operated safely and reliably.